Hey, this is Horner, and we're going to take a look at the free response number 3 for projectile and circular motion review. In this one, you have a couple of students. They build a mechanism that can launch a dense ball, so it's pretty heavy. So there's no air resistance is what they're saying there, and it will land a certain distance into a box is what they want it to do. The launcher works by transferring all the energy that is initially stored in the ball. So we know there's no loss of energy from the spring-loaded device to the kinetic energy to the potential energy at the top. So what we'll have to do here is we know that this is 10 meters per second. We also know that this is 37 degrees. So we need to find out what is the speed in both the x and the y direction. So we're going to break them into components. Here's our bottom component. This is for the x direction. We know that it is constant from left to right because it is a projectile, and projectiles always move at a constant speed from left to right. Up and down, though, they start at a high speed at the bottom, and then as they move up, they go to 0, and then they pick up speed in the negative direction until they hit the ground at a high speed. So if we do 10 cosine of 37, we get 8 meters per second, and that is in the horizontal direction. For the vertical direction, our original speed is 10 times the sine of 37, which is 6 meters per second. So that is in the up direction. At the top it'd be 0, and then when it hits the ground at that instant, so not after it stopped, but at the instant it hits the ground, in the y direction only it's moving at negative 6 meters per second. So what they would like for us to do is also figure out how long it's in the air. In order to do the graphs, you have to know both the initial and the final speeds, as well as you need to know how long it's in the air. So to find out how long it's in the air, we'll use the y direction. We know the final velocity is negative 6, original is 6, gravity is negative 10 because we're saying down is negative, and our time is what we're looking for. If you go through and do the math, you should end up with 1.2 seconds for your total time of flight. Now we can do the graph. We're going to start at 8 for 8 meters per second for the horizontal velocity, and that will go over to here, and that is at 1.2 seconds. Notice it's 2, 4, 6, 8, and then finally 10 here. So, or zero point 0.2, 0.4, 0.6, 0.8, and then 2. This needs to end here. If it doesn't, you'll miss this 1 point for having the 1.2 seconds. In fact, you need to make sure it's 1.2 seconds is where it stops over here too. This is positive 6 and negative 6 meters per second. That makes your slope negative 10, so they're more worried about the slope than they are about where it starts and ends. So you actually could have it start at 10 and then come down, but don't do that. They'll find a way not to give you points, and that is right here where you have to have the specific velocity that you start with. So anyway, those are the 4 points that you will see for this part. For the next part, in letter B, they test their spring-loaded launcher, and when they test that spring-loaded launcher, they find out that it does not go D. Instead, it only goes half of D. And because it only goes half of D, I know this keeps switching, sorry, they try to come up with some explanation. So they test it and they find out it only goes half. They agree that they somehow need to double the launch speed of the ball without changing the angle, but they don't really know how to do that. One person thinks about it in the x direction, says if it has a constant velocity, then the distance is proportional speed, so if you double the speed to double the distance. The other one says, well, but think about delta v is equal to a delta t, and if you can double the time, then that will double the speed. So if you double the launch speed, doubles time in the air, and that will double the distance. Well, are they correct that doubling launch speed without changing the launch angle will double the horizontal distance? And no, they are not correct. The projectile actually goes 4 times further. So if I was to answer this in the PEE format, I'd have to think about it. I'd probably have to do my example and my explanation and then go back and tell how far it goes. So A is correct in that the x direction, if you double the velocity, you will double the position, okay? And that's because of your equation V is equal to delta x over delta t. But our problem here, so here's our equation, but our problem is it's also accelerating in the y direction. So if you double v, you double x, and that's for this equation. And B is correct that if you double v, you double t. So if I double v, I also have to double my t because my gravity is going to still be 10 meters per second squared. In my explanation, now I'm going to say since the velocity in the x direction is equal to the change in position over the double the time, in the change in time, if I double the velocity, I will also double my x. And since the second person said that if I have an acceleration, if I double my velocity, so I'm going to double this guy, and I double the time, that will be a problem because now our acceleration, well, it'll be okay, it'll be the same since a is equal to g. However, if both of these things happen, I'm going to be doubling both the velocity, which will double the distance, and double the time, which will also double the distance. Therefore, if I double the position, okay, so if I double this, and if I have delta x, if I double the velocity and I double the time, I will actually get 4 times the position. So that's where it comes from in terms of the projectile goes 4 times further. I'll do it one more time. If I double in this equation, if I double velocity, okay, if I do that, that will double my x. In this equation, if I double my velocity, it will double my time. And because both of those are true, then I need to look at this equation again and say, well, if I double velocity, I also have to double the time because of the second equation. And if that's true and I double both of those, I will get 4 times the position change. So this one's a little bit harder to explain. Okay, so let's take a look at finally the bottom part here. It says the students do not want to reconstruct their launcher to increase the launch speed, so they instead think, well, it's just half the mass. If I take a ball with half the mass, will it double the launch speed? So the answer is no. They're going to have to change the launcher, and because they don't change the launcher here, it's going to this energy right here is not going to change. So I know that whatever I have here will have to be whatever my speed is. And basically what I can do is I'm going to take off the halves. When I take off both the halves, you'll notice that I have this equation now, and I've half the mass. If I half the mass, okay, and then I go through and I solve for v squared, this is what I get. I get 2kx squared over m, and that's equal to v squared. If I ignore the k and the x squared here, and I solve for my velocity, I'm going to take the square root of both sides, which means that I take the square root of the 2 on the top and a square root of the mass. But we're not really going to do anything with that mass because we know it's mass over 2, and the 2 is now up on the top. And because of that, I get velocity is proportional to the square root of 2 if you take that mass and you half it. Will a ball with half the mass succeeding landing in the box? Okay, and so your answer to this one is absolutely yes. So your answer to I is no. And then if you don't change the launcher, you can't change this, which means that you end up getting a velocity that is proportional to the square root of 2. Okay, so that's what happens to your velocity. But if you have half the mass, okay, and your velocity is square root of 2, remember we also, whatever we do to velocity, same thing has to happen to the time. So we're going to take the square root of the time. If you take the square root of 2 times the square root of 2, you do get 2 times the distance. And that is the end of number 3. Really a complicated problem.